Welcome to Summarize Science, where we break down complex discoveries into simple terms. Today, we are looking at a fascinating paper about how gravitational waves travel through the messy structures of our universe. Gravitational waves are ripples in space-time caused by massive events like black hole collisions. Usually, scientists imagine these waves traveling like straight rays, similar to how we think of light beams. This is called geometric optics, and it works well when the lenses in space are much larger than the wave itself. However, gravitational waves often have very long wavelengths, meaning the ray of light analogy starts to fail. When the wave is about the same size as the lens, things like diffraction and interference become incredibly important. The researchers behind this paper decided to tackle this by viewing the universe as a disordered system. Imagine trying to see through a foggy window. The fog is a collection of tiny, random obstacles that blur the image. They modeled the distribution of weak lenses in space, like stars and dark matter, as a static, random background. To solve this, they used a sophisticated mathematical framework typically found in quantum physics. By using something called a density matrix, they could track how the waves' phase and amplitude change over time. Their study shows that as waves pass through these random lenses, they undergo what is known as quench disorder. This basically means the random environment washes out some of the wave's information. One of the most interesting findings is the concept of decoherence. For a single wave, the path might seem clear, but when you average many realizations of space, the signal appears blurred. This blurring is actually a loss of phase coherence, where the peaks and valleys of the waves no longer align perfectly. The paper describes this as the wave being damped or suppressed by the random structures it encounters. They even identified the specific physical scales that control when this blurring effect starts to happen. This suggests that the wavelength of the gravitational wave and the size of the cosmic lenses must be comparable for the effect to be strong. To test their math, they applied it to a specific type of signal called Gaussian wave packets. They found that more rapidly oscillating waves are affected much more efficiently by the random background. This work isn't just about gravitational waves. The math could also apply to light, sound, or even seismic waves in messy media. So, what does this all mean for the future of astronomy? As we get better at detecting gravitational waves with observatories like LIGO, we will need these models to understand the signals. It means that the blur in a signal might actually contain secret information about the dark matter and stars it passed through. We are moving from simply hearing the ripples to using them as a cosmic ultrasound of the entire universe. This framework provides a unified way to describe interference, diffraction, and random fluctuations all at once. It allows future researchers to probe the power spectrum of matter in the universe using gravitational wave glitches. Understanding these subtle distortions is the next big step in deciphering the history of our cosmos. Thanks for watching Summarize Science, and stay tuned for more breakthroughs made simple.